Lake Tahoe surge, pressure on the devastation fault. It sounds like a headline about water levels in weather alerts, but beneath the surface of this alpine icon lies something far older and far less predictable than a storm. Lake Tahoe is not only a basin of snowmelt and recreation, it is a weight, a force pressing downward on fractured crust that has shifted before and will shift again. The warning signs arrived quietly. A sudden storm, building in the shadow of the Sierra, gathered over the cold blue depths of Lake Tahoe on a Saturday afternoon. Unexpected, powerful, impossible to ignore. In a matter of minutes, the winds shifted, churning the water into 8-foot waves that battered the shore and dragged boats into chaos. By evening, the headlines circled across the west. Lake Tahoe storm kills 8, injures 2 more. Capsize and rescue operations launched in the turbulent waters.
New developments in that deadly boat accident in Lake Tahoe last month. 8 people died when it capsized. 2 others were injured, and now the NTSB has released its findings.
Meteorologist at Ashley Nan Freer stood in front of a satellite mosaic, voice measured. She spoke of a surge, a lake rising to its federally regulated limit, the water overtopping the gauge at 6,229 feet, its absolute maximum capacity. But the water was not the most unusual part. Beneath the surface, hidden below the endless blue, seismic pressure was building. Pressure no storm could relieve. Pressure not measured in rainfall, but in ancient rock, in billions of tons of fresh water, weighing down a fault system with a history of catastrophic disruptions. This is not the beginning of the story, but a chapter in a timeline measured in millennia, marked by ruptures long before memory, events that erased shorelines and left enduring evidence in the landscape. Today, Lake Tahoe is trembling. A major fault capable of magnitude 7.3 devastation runs beneath the lake. The lake's surge, measured and confirmed by geologists and watched by emergency planners, signals a growing concern. What happens when one of North America's most beautiful alpine lakes becomes the epicenter of the next geological disaster? The fault in the lake. To understand what is at stake, you must begin with the weight of ancient pressure. Lake Tahoe, the jewel of the Sierra Nevada, holds about 39 trillion gallons of water. From the surface, the sun glitters off the lake, tourists paddleboard across hidden coves, and the mountains rise behind snow-dusted pines. But beneath the calm, down by dozens or even hundreds of feet, a fault line divides the earth, an invisible gash, a scar that has shaped the region. The Lake Tahoe fault system is not new. It predates the cities on the shoreline and the highways that bring skiers and hikers each season. Over 4,000 years ago, a rupture reshaped the basin, causing landslides to crash into the water, flooding forests and altering shorelines. For decades, geologists have known that Lake Tahoe sits atop a structure capable of major earthquakes. The specific name, devastation fault, doesn't appear in official literature, but the reality is no less serious. A fault with a simple equation: long intervals between ruptures, immense weight above, and increasingly close attention from scientists and planners. The water itself is part of the danger. Billions of tons, enough weight to press down the Earth's crust, adding stress to every microfracture. Each drop is part of a lever, magnifying pressure along the fault. The events of the past week brought this long drama to a sharp point. On that Saturday, the surge reached 6,229 feet, the absolute upper legal limit of the lake. Water lapped at docks and low-lying neighborhoods, and beneath it all, the fault felt the weight. Lake Tahoe has never been just a lake. It is a basin filled to the brim, its stability never fully assured. What will it take to cause the next shift? A surge no one expected. The 6,229-foot surge was not predicted. The weather models, with their detailed analyses, failed to anticipate a system so swift, so forceful, so disruptive. Locals, accustomed to Tahoe's variable climate, watched the skies and braced for another storm. April storms are common and usually manageable, but this was different. Winds howled across the lake's 22-mile expanse, compressing water against the far shore. In less than half an hour, Tahoe's familiar surface became a heaving expanse. 8-foot waves pulled buoys free, snapped lines, and battered boats. A boat, crewed by tourists, capsized near Emerald Bay. In the chaos, efforts to deploy life jackets failed. 8 lives lost, 2 injured. But the surge was not merely weather-driven. Geologists monitoring the shoreline noticed something stranger still. The lake's level, which had been steady just below its regulatory maximum, suddenly spiked by a notable margin. No atmospheric river, no sustained snowmelt or rainfall system could fully account for the rise. Phone calls began. Across the United States Geological Survey, from Menlo Park to Reno, a new question echoed. Where did all this water come from? The surge, first dismissed as a temporary anomaly, lingered. Exceeding the 6,229-foot mark has legal and practical consequences. Flood warnings, emergency declarations, mobilization of local disaster plans. Sandbags stacked, roads closed, dock owners called their insurers. But for seismologists, the real concern lay not in the water, but in the growing tectonic pressure below. Lake Tahoe's level has rarely stayed this high for so long. The pressure on the underlying faults has rarely been greater. Is the surge itself a symptom or a sign of things to come? Pressure builds in the abyss. Underneath the sparkling surface, Lake Tahoe is a vertical world. Its maximum depth is 1,645 feet, deep enough to submerge city skylines, deep enough that its mysteries are measured mainly with sonar and remote sensors. 39 trillion gallons. This volume is not uniform. Ages of flood, drought, avalanche, and earthquake have sculpted the lake bed into shelves, cliffs, and hidden canyons. Underwater landslides, sometimes triggered by distant tremors, have sent tons of debris tumbling into darkness, subtly altering the bottom's shape. Beneath it all, the main faults remain. The lake's water exerts a force measured in billions of tons, pressing ever downward. Each season of snowmelt, each rise in water level adds to that weight, an ongoing load amplifying the stress along the fault system. The fault zone is not a single, clean break, but a complex region of fractures visible only through seismic data and geological mapping. Following the 6,229-foot surge, seismic sensors registered upticks in microtremors, tiny, non-destructive earthquakes, the Earth's faint response to increasing stress. Scientists interpret these as signals, a chorus that may be warning, release, or just the ongoing background motion of a stressed system. By geologists' best estimates, the main Tahoe faults are overdue for a major event on scales much longer than human memory. The last of these major ruptures transformed the basin as underwater landslides shuffled sediments and old trees along the shore died in clusters. If the system fails again and the Earth's stresses combine in the wrong ways, the magnitude could reach 7.3. Few, if any, living around the lake have a true understanding of what that would mean. Are the warning signs already visible? The edge of catastrophe. Standing on the shore of Lake Tahoe is to witness stillness and underlying tension. But every community here is built on ground shaped by unpredictable forces, maintained by the assumption that the Earth will not shift and the waters will not rise above control. The regulatory maximum, 6,229 feet, is a hard limit. It was determined through careful hydrological and risk-based calculations, a line at which flood planners begin mandatory evacuation checklists. Surges to this height can flood roads and homes. They force water into meadows that buffer infrastructure, erode bridges, and seep under shoreline highways. Recent surges have forced emergency planners into action. But the truest risk lies deeper, the relationship between water level and seismic stress. If a major earthquake occurs beneath the lake, the immediate consequence is a shock in the water, moving energy through saturated soils. The weight of billions of tons of water amplifies the effects, translating fault movement into underwater slides, waves, and pulses that can affect the shore. Tree rings and sediment cores along Tahoe reveal the evidence of ancient disasters, forest die-offs, and abrupt layers of underwater debris. A 7.3 magnitude quake beneath Tahoe would redraw the region's physical and social landscape. Tsunamis on a mountain lake may sound rare, but geological models show that they are a tangible risk. Walls of water up to 30 feet high could strike the shore, inundating harbors and low-lying areas. What do the latest models suggest? What happens if a critical surge coincides with a fault slip? Is such a future preventable or simply delayed? The mathematics of overdue disaster. It's not just that the Tahoe faults are overdue for rupture, it's that the probabilities rise as stresses accumulate. Geologic records are imprecise. They come from layers of mud and ancient trees buried by landslides, from sediment scattered by earthquake-triggered avalanches. The last major rupture of the main Tahoe faults is estimated to have happened more than 4,000 years ago, before written history in the region, before the world as we know it. Since then, water levels have risen and fallen with the climate. But never have so many people, so much infrastructure, so many expectations been built atop so much water, so close to a critical geological structure. The surge to 6,229 feet is not just statistical noise. It is the top allowed by federal regulation, a number that triggers coordinated flood response from county agencies to the Army Corps of Engineers. Lake Tahoe is subject to the same calculations as all lakes: input, output, evaporation, and runoff. Yet its vastness magnifies every shift in supply and demand for water. And when water pushes directly downward on stressed faults, research suggests the risk of earthquakes can rise. 1 billion gallons equals about 8.3 million tons. With 39 trillion gallons in the lake, the crust below supports over 323 trillion tons of water pressure. Researchers in earthquake science note the links between high water tables, sudden surges, and a rising tendency for earthquakes in stressed regions. Surges driven by rare storms, rapid snowmelt, or persistent high water marks may increase the odds, even if not in a linear way, for sudden seismic events. Lake Tahoe's recent surge is a warning. Each extreme, each year at max capacity, adds to the unique circumstances that could eventually trigger a geologic event. Are the clues mounting? Does geology remember what people have overlooked? Unraveling the anomaly. Scientists speak cautiously, in probabilities, with error bars, acknowledging what they do not know. But the recent surge at Lake Tahoe has confounded expectations. Where exactly did all the extra water originate? Measurements from gauge stations along the Truckee River and its snowpack monitors don't add up to the observed spike. Some propose that very slight changes in the lake bed, tiny uplifts or subtle underwater landslides, may have briefly altered Tahoe's capacity. Others wonder if water pooling from earlier storms or hardcore runoff joined the main body suddenly, accounting for the rapid rise. But these explanations are, so far, hypothetical. No scientist can say with certainty that they know the precise sequence. What is clear is that the data do not fit the models. Locals have taken note as well. Old-timers recall floods and snowpacks of winters past, but find no memory of a spring quite like this one. Dock pilings strain as water pushes against them, and through it all, the lake holds near its legal maximum. How long can such an anomaly last? And what does it mean for the future of Tahoe's equilibrium? Communities on the brink. Every town along Tahoe's shore is a balancing act, an attempt to live alongside the region's legendary beauty and its periodic peril, to build an economy on tourism and recreation while managing the unpredictable cycles of water and geologic risk. South Lake Tahoe, population roughly 22,000, is a mix of hotels, casinos, residents, and seasonal workers. Every winter and summer, crowds fill the city, drawn by the promise of snow or sun and the inviting blue water. But the regional economy is based on certain expectations: that the lake stays within safe limits, the roads remain passable, the beaches open, the slopes and hiking trails accessible. The recent surge tested those assumptions. Boat rentals halted, marinas sent staff home, tourists asked for refunds as beaches disappeared beneath high water and mudslides disrupted trails. But it is the hidden risk, the quiet, underlying threat that is catching up with the region. Insurance companies are reassessing their models for flood-prone properties. Homeowners in Incline Village and Kings Beach receive notices. Premiums could rise based on new data. Service economy workers, a backbone of the region, worry about fewer bookings, less work, and a fragile safety net. And behind the scenes, emergency planners are coordinating, preparing for possible mass casualty scenarios. The surge and the recent storm-related deaths have changed perceptions. These are not routine events, and the systems holding back disaster are under stress. Conversations in homes and businesses shift. If a major seismic event ever occurs, what can any one community or individual do? Is the area prepared for what may come, or just waiting? The unsaid calculations. Certain facts never appear in press releases. They are studied late at night by planners, referenced in quiet briefings, spoken about frankly only among those who must prepare for the worst. Lake Tahoe's surge to 6,229 feet is not just a warning about water. It is an indication that the status quo cannot be taken for granted. In offices of the USGS and emergency management agencies, scenarios are updated. A magnitude 7.3 event under the lake, modeled by experts, triggers widespread infrastructure failures within minutes. Shoreline bridges, water lines, and power grids are vulnerable to floods and liquefaction. Immediate evacuations become complex as mountainous roads narrow and low-lying safe zones fill with water. What follows? As recent history has shown, information lags reality.
A tsunami on Tahoe would look different than one at sea, but could devastate harbors, homes, and businesses within its path. Infrastructures, power, phones, internet, are robust enough for snowstorms, but not necessarily for massive shockwaves or wall-like surges of water. Federal and state aid would respond, but geography is unforgiving, and critical moments would be lost in the scramble for reconnaissance and the mobilization of resources. Most people would not know the event's full scale until long after it had begun. No planner claims readiness for every possible scenario. The latest surge and the persistent record-high water make it clear Lake Tahoe's risks are rising, and the old models may no longer hold. Can preparedness keep up when disasters threaten at a scale not seen in living memory? Waiting for the next pulse. The lake is calm now, but tension grows as the high water lingers week after week. Marinas are monitored for damage. Park rangers and local police check for new signs of collapse along the shoreline. Survey teams use sonar to search for evidence of underwater slides that could hint at renewed movement at depth. Every storm and each early snowmelt adds pressure, drop by drop, on a system already pushed to its limits. Most of the public, denied access to classified risk assessments, receive only general updates. The deeper story,
read by those who interpret seismic graphs, is not publicized. The facts remain. Lake Tahoe is now as high as engineers allow. Beneath it, the main faults carry historic pressure. Tourists return, seeking beauty and recreation, but the faint sense of unease endures, felt by workers, residents, and those quietly tracking the lake level's every move. The state waits for the next sign, the next surge, the next moment when nature and geology align in unpredictable ways. Is this the season, the year, the week, or are the warning tremors already underway? At the water's edge, 6,229 feet. The number is etched on technical reports and on warning signs beside the highest docks and in low-lying neighborhoods. The story told to visitors is of resilience, a region that rebuilds after wildfires and snowstorms, that adapts to new weather extremes. But water does not negotiate. The surge has rewritten expectations. The storm, the tragic losses, and the silent, ongoing addition of pressure onto long, restless faults have changed the risk equation. No one can predict the timing of the next fault slip. No one can guarantee that another surge will not tip some balance. What is certain is that Lake Tahoe is more than water. It holds memories of ancient disasters, pressure from modern management, and warnings as urgent as those issued by science or policy. The faults have waited millennia. The latest surge is part of an ancient dialogue: earth, water, and stress, unresolved. In meetings, in homes, and among scientists, one question prevails. Is there time left to prepare, or are we simply witnessing the latest, and perhaps final, warning sign from Lake Tahoe?